Hey everyone, welcome to Saturday Night SQL Virtual Group webinar. My name is Sarah Huang. I'm the founder and organizer of this virtual group. Joining me here is Debbie Huang, our co-organizer. Today, Aaron Kashal will present an exciting topic called There Be Wheels Here, Big Data in SQL Server for our virtual group. Aaron Kashal is a senior data architect with 20 years of experience in analysis, design, and development for applications and databases in manufacturing and warehousing, plus over 10 years in the healthcare informatics field. His primary focus has been in the field of clinical quality measurements utilizing very large databases that involve millions of patient records. He is the leader of his PASS local group, IndiePass, and actively speaks at SQL Saturday sessions across the country. We really appreciate Aaron spent his Saturday night to share knowledge with us. Let me first go through the PASS community news, then transfer screen over to Aaron. PASS is looking to connect with the new sponsors. If you could help PASS expand the research and the reach and receive, you'll get $100 gift card for referrals leading to community sponsors. For more information, please contact Catherine Allen at catherine.allen@sqlpass.org. Also, PASS is your invitation to a global community of 250,000 like-minded data professionals who leverage the Microsoft Data Platform. If you're a member, you can unlock incredible year-round learning and professional development opportunities, such as virtual group webinars and in-person networking, etc. PASS also has a career center for job hunters and employers. You can check it out at pass.org/careers. PASS Summit 2018 is calling for speakers, and the deadline to submit the abstract is on March 21st at 2000 UTC. PASS Facebook Live for March is on 27th, and the expert is Kendra Little. It's on the 27th and 1800 UTC. And you can like and follow the PASS Facebook page to reserve this event. Oops. Okay. So you may know already, PASS has a new offering this year for the PASS Summit 2018 registration. As a Saturday Night SQL Virtual Group member, you can use this code VGSTRP9II to register for the event and get free streaming access to all of the PASS Summit 2017 content. These are the upcoming virtual group webinars, and tonight is our virtual group, and on the 13th, Women in Technology, then Data Architect Cloud, and we will have another session again on the 24th, which is Azure Machine Learning Studio. Then there are other virtual groups also have different kind of interesting topics. These are the upcoming SQL Saturday events. Check it out at sqlsaturday.org.com to register for the event near you. And PAS has many virtual groups, and you may join as many as you would like. PAS membership is completely free. As always, you're more than welcome to join our virtual group. This is our Saturday Night SQL. Oops, sorry. This is how you may connect with the PAS through Facebook, Twitter, or LinkedIn. This is the Twitter handle. If you would like to ask questions, please use this little hand sign to get our attention. We'll unmute you so you can interact directly with Aaron. Otherwise, you can enter your question in this little chat window. I'll read your questions to Aaron. Thank you so much. Let me transfer screen over to Aaron. And thank you, Aaron, for taking the night, spend your Saturday to share your knowledge with us. We really appreciate it.
Not a problem at all. Can you see my screen okay?
Yes.
Okay, super. So I'm happy to be here, and I appreciate the opportunity to speak to you tonight. I will have to say that this is a bit of a different scenario for me. I'm used to presenting in front of a live audience. Not that you guys aren't live, but that I can't see you. So hopefully we will still engender a bit of interactiveness with this. So if you have questions, please feel free to ask them in the chat window, or we'll also have a pause midway through for questions and also at the end. But if you have a really burning desire to ask that question, then please, by all means, let's ask it. I should clarify too that I am no longer the chapter leader for IndiePass since I moved to South Carolina. So unfortunately, they're doing a great job going on without me, but unfortunately, I'm not able to be there to work with them. So let's talk about why you're here tonight. And so you want to know what big data is on SQL Server. And as you can imagine, I took the title of this, there be whales here from Star Trek 4. So, when Scotty announces that the whales have arrived. And whales do indeed represent a big data because they are so large. So again, a bit about myself. Sarah had already mentioned it, but I've got 30 years experience in the IT industry, more specifically with databases and of course SQL Server, mostly in the last 20 plus years. I do have a few degrees. Last one was in health informatics, I guess because I couldn't get enough of it or something. Currently, I'm the senior data architect for a company called Global Emergency Response, and we develop solutions for emergency and disaster recovery, patient tracking, and management. And as Sarah mentioned, I do speak at SQL Saturday events all across this country, and also in various local chapters, and now online webinars. And I have contact information here if you'd like to reach out and ask me additional questions, and I'll have that information again posted a little bit later on. And as Sarah explained to me, that these slides will be made available to you. And I should tell you now that there are some links in the slides for a lot of the references that we'll be making in here to other articles. And so I invite you to take a look at the slides and follow those links and look at the articles that we're going to be referencing. So let's talk about what we're going to cover tonight. First of all is the question, what is big data? And that, believe it or not, is a very loaded question. We're going to cover some definitions for what big data is and also review some common myths that exist about big data. And then we're going to take a look at a few case studies when big data goes bad. We have a scenario here for SQL Server versus MongoDB and also one versus Hadoop. And then we'll review those with some observations that we made from that. And then after our halfway point, we're going to cover what big data is for SQL Server and look at a case for a project that I worked on called CoreAnalytics. So I'll give an overview of what that project is so you get an idea of the mass of the scale of what data is going to be involved. And then we'll cover the big data techniques that are used to make this project really hum. And that involves table structures and queries, T-SQL coding, indexes, partitions, etc. And we're going to look at some alternative options that we could have used, but did not for some other reasons. Alternatives that were probably quite viable as well. And then at the end, again, we'll have an opportunity to close up with some thoughts on that, on what we discussed, and ask questions and get some answers to those. So what is big data? Let's take a look at some definitions here. The Oxford English Dictionary gave a definition that it was extremely large data sets that may be analyzed computationally to reveal patterns, trends, and associations, especially relating to human behavior and interactions. Now, I find this description or this definition to be a bit vague. It has some things in it that we want to pay attention to. So I pulled out some keywords such as large, analyze, patterns, trends, associations. Those are some of the keywords that we would be most likely to associate with big data. Let's take a look at another one. This is from the Merriam-Webster Dictionary. An accumulation of data that is too large and complex for processing by traditional database management tools. I don't know what they were smoking there, but this is basically saying that big data cannot be processed by anything that we already have. And we'll touch on that point a bit later on too. But here's some keywords, again, about accumulation, large, and complex. So you can kind of begin to see a trend forming. Gartner research said it's high volume, high velocity, and or high variety information assets that demand cost-effective, innovative forms of information processing that enable enhanced insight, decision-making, and process automation. And I tell you, that sounds like it was written by CEOs. It really does, because it's a lot of the buzzwords, but it doesn't really say a whole lot. But here's some of the key words that are key to point out. High volume, high velocity, high variety. Those are some of the V's that we're going to cover a little bit later. Cost-effective, innovative, enhanced insight, decision-making, and process automation. Some of these are applicable, but by themselves, just strung together, it doesn't really tell us what big data is. And so MIT, you'd think they would have a really good handle on it. And they described it as big data is a term describing the storage and analysis of large and or complex data sets using a series of techniques including but not limited to NoSQL, MapReduce, and machine learning. Okay, so this is a good description of what we do with big data, but it still doesn't give a good description of big data other than the fact that it might be large and or complex data sets. So again, we're going to pull out some keywords of storage, analysis, large, complex. Again, those words come up quite a bit. And then here's some references to NoSQL, MapReduce, and machine learning. Now, let's take a look at some reality. The definition of big data is a moving target. And I should point out, too, that all of these phrases that are underlined, that are in green, these are the hyperlinks that you want to take a look at and read those articles to see what I'm talking about here. But it's true, big data, the definition is moving, constantly changing, and it always depends upon who is saying what it is. Berkeley University did a survey of 40 industry thought leaders and asked them the question, what is big data? And not surprisingly, not one of them agreed with another. Most people think they understand what big data is, but it's really skewed by their perspective, by how they view it from their point of view, how they interact with it, what they perceive in their workspace. So let's look at some defined characteristics of big data. First of all, the 3 V's that we mentioned earlier: volume, variety, and velocity. How much data we have, how many different kinds of data we have, and how fast is that data coming in. Now, a lot of people also attach 4 additional V's to it: veracity, variability, visualization, and value. Veracity is basically, how well defined is the data? How can you be sure it's accurate? Variability, of course, is in changes to how, not to be confused with variety. Variability is in, sometimes you may have some data, you may have others, you may have a lot. It may ebb and flow a bit in how it comes in. Visualization, that really speaks more to what you do with results, not really with the data itself. And value is something that's very subjective. That's based upon, what someone may consider it to be of value, or what, and I don't necessarily mean a monetary price tag on it, but how important is that data? One of the things that confuse people when it comes to big data is the distinction between structured and unstructured. I mean, there are huge disagreements on what that definition is. And if you stop and think about it, if you look at a form, in any type of form that you fill out and you write in on the blanks, even at the DMV or whatever, that is structured data. But take a letter, for example, that has no particular structure to it, no form, it's just written out in paragraphs and sentences, etc. That would be a definition of unstructured. So let's take a look at some myths that are involved in big data. One of them is that big data is a new phenomenon that only came about in recent years. Well, that's not true, because there are some very large projects that use a lot of massive data, such as the genome database that maps to human DNA. They've been using relational database management systems for most of the entire project. If you want to talk about large data set, how about the astronomical data model? That's a relational data system that's been in use for many years, long before PCs were around. So it doesn't mean that because you have a lot of data, doesn't mean that you cannot use a relational database management system. And they've been around for a very long time. Here's another myth. To process big data requires totally new platforms and thought processes. Yeah, these are the people that are also trying to sell, things that you're going to have to make a whole new door to put it through. These are marketing articles targeted toward, your CEOs and CFOs, etc. And they're trying to entice them into spending more money, into, to buy, vendor product A and B, or whatever the case may be. And they do this by promoting the myth that companies will not survive without embracing big data. So companies such as, that are selling Hadoop solutions, or any of the other NoSQL products, they're trying to encourage people to buy their product, and these myths help encourage that. Another myth is that because big data is so large, it can be difficult to process. Well, really, people get the complexity and volume mixed up. So complexity is more due to how the data is organized than it is by the volume. And it's really a myth that only NoSQL platforms can handle big data, because it all depends on how it's structured and how it is organized. NoSQL vendors and training companies promote myths like Hobbes is to Calvin, Hadoop is to big data. They're trying to make associations so that, you think of one, you think of something else. So if you think of big data, boom, you think of Hadoop or something of that nature. And they're trying, again, to sell services and products. And so it's in their best interest to promote these kinds of myths. Another one that's really, really annoying is that some people say that big data applications require little or no performance tuning. I mean, really? I mean, if you stop and think about it, all data systems require tuning for proper performance. It doesn't matter if it's SQL Server or Hadoop or Oracle, whatever it is. you have to tune it to meet your specific requirements and your specific situation. After all, remember how well plug and play became plug and pray? I mean, it doesn't work that well. It sounds great, but it's not really a reality. And here's another one. Analytics requires big data. And so somehow they've got it into people's heads that in order to perform any type of analytics, you have to have big data. Well, if you stop and think about it, analytics has been performed for years in relational database management environments, and long before Hadoop was even thought of. And insurance companies have even had them far longer. They've had people called actuaries who are really data scientists, if you stop and think about it. Another myth is that big data is only unstructured data. And again, it comes back to that confusion between unstructured and non-discrete. So in reality, structure is imposed on your data one way or another, either when you store it, such as in a relational database management system, or when you retrieve the data, like you have to do in a NoSQL environment. One of the proponents for NoSQL data environments is that you don't have to structure the data. It can take data in any format, and that is true, and it really does a good job with that. However, in order to make use of that data, you have to know what that structure is at some point. So whether you're storing the data in a structured fashion, or when you go to query the data and you need to know, how do I retrieve that data? How do I search for what I'm looking for? Then you have to put the structure into it at that point. Of course, one of the biggest myths of all is that big data is too big for SQL. If we stop and look at the massively parallel processing platforms that support the parallel processing and also SQL, and we're talking about Netezza, Teradata, Azure, etc. All of these platforms support and use big data as well as SQL. And in fact, if that weren't the case, most NoSQL environments now are having SQL interfaces. Now, those SQL interfaces are not designed in the same way that it is for a relational database management system, such as SQL Server. It's not optimized for it, but they do have an interface to make things work and to make it as a convenience for people. So let's take a look at some scenarios here. For example, here's one with MongoDB. Now, this is an environment that I was introduced to some time ago. So this involves clinical quality measures. And as Sarah mentioned, I've been working for 12 years now in healthcare, and clinical quality measures is a very big part of that. And what this is basically we're going to identify what a denominator is. So what it is that we're going to measure, such as people who are diabetic. And then we're going to look at the numerator, so which is considered the measure itself, such as if a person is diabetic, did they get a retinal eye exam in the last 12 months? And so either you did or you didn't. It's a pass-fail scenario. And again, here's that example of patients with a retinal eye exam. To make it even more complicated is that clinical data is identified by a pair of codes, what known as a taxonomy and a term. And then the taxonomy refers to a type of code system, and the term would be that code value. And the data is also then identified by various categories, such as encounters, diagnoses, procedures, medications, etc. And so all of this data is broken up into very distinctive categories. So you can imagine how complex the data is for those of you who are not in healthcare. So they wanted to implement this clinical quality system, so they did so in MongoDB because it's a NoSQL environment. It should handle the large volumes of data. So they had 40 clinical quality measures of varying complexity, and they had data for about 750,000 patients in their test environment. Now, the data was stored in XML documents, which is referred to as the clinical data architecture. And this is a very common way of passing patient data from system to system. And one document per patient contains all known data about that patient, including their history. So they took that data for 750,000 patients and they sharded it across 10 different MongoDB servers so they could get some parallel processing going there. They used Ruby on Rails for their processing logic. And keep in mind that MongoDB does not have an equivalent of T-SQL. So you have to use some other processing system to do that. So they used Ruby on Rails. And they were able to generate results for those 40 clinical quality measures in about 8 hours. Now let's compare this to a version of SQL Server that I developed. So I took the same 40 clinical quality measures, and this time I had data for 2.5 million patients, and this was stored on my laptop, so I didn't have 10 servers to shard the data across. I did normalize the data, broke it out into elements and attributes, and I did load only the data that was required for the measure calculations. So I did some data massaging ahead of time. I didn't take the entire clinical document architecture format and load everything into the system. I used T-SQL and set-based processing logic because that's the whole premise behind SQL Server, is to do things in a set. And I was able to generate results in about 45 minutes for 2.5 million patients. And for some reason, they didn't believe me. So why was there such a big discrepancy between them? Well, first of all, MongoDB relied upon procedural processing. So basically what they did is in their Ruby on Rails code, they searched through each of the documents. Now, this was a few years ago, and I'm sure that MongoDB has evolved since then. But they basically would go through all of the documents looking for the specific data that they needed. And so they didn't have any correlation also from one patient to another because it's not a relational system. And so, and they also could not search across the document. So it required each document to be reviewed for each measure. Now, healthcare data is highly structured and it's relational, and by its very nature, because you have, a patient is related to an encounter, and during that encounter, there will be various procedures, examinations, medications, diagnoses, etc. So there is a lot of highly relational data there. So in SQL Server, I also focused only on what data was needed, and I used the set-based processing. And I was able to perform a single measure of all those 40 measures against all 2.5 million patients. And unfortunately, on the MongoDB version, they were looping through each patient for each measure, and because they were trying to apply the logic very much in a procedural fashion. So let's take a look at another one. And this was another project I worked on that they were moving some data from, or moving a system from SQL Server to Hadoop, because they want to be able to analyze claims, and this is in a insurance process. Analyze claims before payment so they could look for different scenarios that identified fraud, waste, and abuse and billing errors. And the claims had to be paid within 24 hours of receipt. This was a business requirement. So as you can imagine, time was of the essence here. The claims analyst reviewed the generated recommendations that the system performed before submitting the final approval for payment. And approximately 150 analytical concepts of varying complexity were used. And each one of them looked at a different scenario, and each suspect claim was required to have one or more reference claims to support that. So you can imagine that this was pretty complex in of itself. So for example, you could look at a cataract surgery. I mean, they're allowed in one eye or each eye only once, because you can't have a cataract replacement in the same eye twice. On the SQL Server version, and this was built before I came along, what they did is that in order to process these concepts, they took the data from the claims processing server once a day after midnight, and unfortunately, they copied it as it was for the claims processing system. They did not update it for this type of an analysis. They didn't modify the data structures. The tables were the same. They used basically text keys, etc. It was a very poorly designed architecture for this type of operation. They had large records for the claim header and detail because they believed in using, 150 different columns in a table. Again, most of the data was text, including the primary and foreign keys, so that slowed down the data matches. And with all of that, it was not optimized for this analysis. And each store procedure was written for each scenario, and they were not written by developers. They were written by business analysts who did not have a good understanding of T-SQL, let alone SQL or even the data structures. And because of that, they were written by different people. The way they were written was very inconsistent. They were not optimal. Some of the logic in there was just really, really bad. And so the procedures took a considerable time to execute. Very few of them completed within an hour. And there were quite a few that did not complete in the 24-hour time frame that they had to have them in. And so unfortunately, a lot of checks were written before this analysis could be completed. So somebody got the idea that, well, if this is so bad and this is so slow, let's just take the whole thing and pick it up and move it over into Hadoop. Because Hadoop is fast, right? That's what they were thinking. Well, one of the first things they did was they came up with the idea to capture the data as a live feed from the original claims processing system. That was an excellent idea, very well implemented. Wish they would have done that on the SQL Server version. However, they kept the same data structures that the SQL Server version had. They didn't optimize it for analysis or for the kind of concepts that they were trying to figure out. They even took the same store procedures and kept it mostly as it was. They didn't even go into why were things being done the way they were being done. They just took the code, moved it over, and put it into Hive SQL. They did have to do some workarounds because in Hive SQL, because of the way Hadoop works, there is no concept of an update or delete in the data. So they had to do some workarounds for that. And that really involved basically creating new tables to omit records or to update records and rewrite the entire table all over again. Initially, they only worked on the most simple concepts or the scenarios that they wanted to work on. And some of them, they did get some time savings. But the whole idea behind putting it on Hadoop was so they could do more than one execution in a day. And they couldn't get more than just one. So why did this fail? Why did it not work out? Again, first of all, the data architecture was not optimized for analysis. The store procedures weren't optimized for performance, mainly because they were created not by developers, but by business analysts who did not understand TSQL. And there was very little direction in how things were to be performed. The business logic wasn't very well documented. There was either no documentation or very vague documentation on why things were being done. The other problem was that Hadoop was chosen for its speed, and yet SQL was used for the application interface. So Hadoop is not designed to work natively with SQL because the SQL interface is it's meant more for convenience than it is for performance. And the choice was made by the executives without any analysis to what the problem was, why it was an issue on SQL Server. They just said, well, let's just put it on Hadoop. Now, had they taken that time, energy, and effort and the money and put that onto the original implementation and corrected the problems that they had in the SQL Server version, the project would have been completed a lot sooner. I mean, the project went over a year and still wasn't completed. They could have finished it in about 6 months and with a lot less cost. So let's take a look at some observations about these two scenarios. The biggest one is that the platform was chosen to be considered, or the platform that was chosen was thought of as the solution itself. Instead of looking into the data architecture or how the data was being used or what the data was even, they just said, well, we got to go with the NoSQL solution. So they picked that. So no real analysis was performed on the other approaches at all. Management, again, picked the platform. It wasn't IT management either. It was done by people who thought, well, this has high visibility. We want to be impressive. And if it's successful, then we're all going to look like heroes. And the biggest problem was that they think, but it's free. I mean, Hadoop is free, right? You can just download it, right? But the problem is that there's a hidden cost to free. And a lot of that involves not just how to obtain the software, but in the time to use it, the support costs, etc. So take a look at that article when you get the slides. It's a real eye-opener about the hidden cost of free. And also, there was no root cause analysis performed to determine what was really the problem in the original solution. They thought, well, the problem must be in the data or the programming. So therefore, that's something that can always be worked around, right? You can just always tweak some code. And so when things didn't go right, they decided to have all-day meetings to, let's see if we can't improve productivity by having more meetings. Maybe it was just because it was a big company, but that never seems to go anywhere. The end result is that you pick the wrong tool for the wrong job or use that tool incorrectly. It will not get you what you want. My dad was always a big believer in using the right tool for the right job, and he impressed that upon me. Just because you can use a screwdriver as a chisel doesn't mean you should. So let's take a look at what we've talked about. We've covered so far is the question of what is big data, the definitions of big data and how disparate they are, how no one can seem to agree, and also about the common myths that are circling big data and what people are forced to think about that in terms of the associations of big data and the marketing attempts to change those myths. And then we looked at the case studies about when big data goes bad. We looked at the MongoDB and the Hadoop environments versus SQL Server and covered those observations. And I would like to open the floor at this point to anyone who has questions over what we talked about before we get into the big data on SQL Server aspect of it.
Hey, Aaron, I haven't seen any questions so far, but I do have a quick question.
Sure.
When in choosing the tools for the data, then you mentioned those two cases scenarios, how what are the criteria in in choosing which one is the right one to use?
Well, in these particular cases, people pick the tool because they want to look like they're, on the bleeding edge of technology. And so, Hadoop is the big buzzword. Big data is the thing. So let's go with that approach. And if you use anything with big data, then we got to be using Hadoop. So that's why the executives pick that tool. The real thing to do is to analyze what your data is, how it is moving, what functions need to be performed on it, and based upon that, then you choose the tool that's appropriate for it. In many cases, Hadoop is the right tool for that job. In other cases, it's not. Uh, and I don't want to make it sound like I'm anti NoSQL environments. I'm not. I'm just saying that people need to stop and think and really determine what solution they want. It's for the same reason that SQL Server is not always the best solution for data processing. It sometimes is not. Sometimes you need to use Hadoop. So you always want to look at all aspects of it before choosing what your platform is or what your tool is.
Yeah, sounds great. We got a question asking, do you have any book recommendation for big data with SQL Server?
I'm glad you asked that, because when I was doing research for this presentation, I was really shocked at how little information there is about big data outside of Hadoop. And because there was always this knee-jerk association between big data and Hadoop. You can't have one without the other. And but when I looked at SQL Server implementations with large volumes of data, there wasn't really much written about it. Not that it doesn't exist, because as I identified, there are other various scenarios where SQL Server is used for large amounts of data. But I think it's because it was not considered to be extraordinary. It was not considered to be something to write a book about, because they thought, well, it's just a volume of data, it's bigger than what some others are. For example, Salesforce, huge company. They deal with a lot of data, terabytes of data, petabytes of data, and they do it all in SQL Server. And you would think that they would go with Hadoop, but no, they found that SQL Server actually performs better for what they need.
Well, I guess it needs this POC, right? But
yes,
before we can make sure which one is a good choice. We got another question. It says usually mentioned 3 V's for big data. Does it need to fit all V's to be considered as a big data?
Not necessarily. Those V's are characteristics of big data, but just because one of them may be missing doesn't mean that it wouldn't be considered big data. Again, SQL Server can handle large volumes, fast moving data. In fact, because it's a transactional processing system, it can handle things faster than what Hadoop can at times. So a lot of times, they will take data from transactional processing systems in SQL Server and then pass it over to a data warehouse environment.
Okay. Thank you. If we would like to do the machine learning, can SQL Server be a good platform for this need?
I have seen SQL Server used for that. Mostly they use the analysis services for machine learning, but I have attended several presentations that showcase machine learning from SQL Server. So yes, it could be a good platform. Again, you want to do your due diligence and take a look at the environment that you have, what needs you have, how fast your data is going to be coming in. Most machine learning is done on an after the fact area, so it's like a copy of what's in the production data that is used in for analysis. So it could be a good platform for you.
Cool. Yeah, my company is using the SQL Server for machine learning. Anyhow, I think that's all the questions we got so far. Oh, another one just came in. When should we choose big data instead of RDBMS if volume is not just a constraint?
So if volume is not the only constraint, one of the things that that you want to consider about when it comes to big data, take for example NASA. All right, when they're getting data from, say, the Voyager probe or whatever it is that they send out, they can't say, "What? Wait a minute, hold on. Let me figure out what kind of structure we're going to use for this data and build a database and then put in. Okay, now you can send it to me." No, they just capture that data as it's needed. So it can come in many different formats and can be considered unstructured. So Hadoop is a great environment for storing that kind of data. And then once you do have determined what your structure is, what a lot of places are doing now is that they're using taking Hadoop data, loading it into SQL Server so they can perform that analysis instead of doing it within Hadoop. Because in Hadoop, you always have to search for that data and find it, and you're always having to rediscover it, so to speak. It's kind of like if you always had to read text files to get your records, and you always had to search and do string searches and string manipulation, etc., to get your data. Whereas if you load it once, go through that process just once and load it into a table, in a relational table, then you could do much faster analysis with it. So that's what they're doing a lot of now. And so they're using a blend of NoSQL and SQL Server.
So you would think the combination of NoSQL plus SQL Server is better?
Oh, I wouldn't say better for all scenarios, but for situations like that, with I mentioned with NASA, it's a great combination. There is no reason why these platforms cannot be used in conjunction with each other.
Okay, makes sense. I think that's all we have so far.
Okay, cool. All right, so let's talk about what's coming up next. So we have big data for SQL Server. How did we do something like that? So we're going to cover things such as table structures and partitioning, keys and indexes, querying large data volumes, and taking a look at some store procedure techniques. So the project that I did this on was called CoreAnalytics, and again, it involved healthcare measures. And as I mentioned before about the clinical quality measures, measured the quality of patient care and adherence to quality standards. And utilization was more focused on cost or performance efficiency of a healthcare facility, such as, when patients were processed through the emergency room in a hospital where they'd done so in a more cost-effective manner. The clients for this were major healthcare provider systems. We're talking about hospital networks that had data for about 70 plus hospitals, and each hospital had hundreds of millions of patients in their clinical data. We had about 20 or more clinical quality measures, 10 or more utilization measures. And with all of this terabytes of data, we were able to perform a calculation in about 1 to 2 hours. So how did we do it? The other thing I should mention is that the measure calculation engine was designed such that the definition of the measures were created and or edited by non-programmers, and they were stored as structured XML documents. And once those measures were defined, they were then compiled into stored procedures. So it had a process in place that would take the the measure definition, and create efficient store procedures out of those. The data was imported from various electronic health records or electronic medical record systems. And instead of trying to map the system to whatever data we had coming in, we changed the data itself and mapped it to standardized taxonomies and terms. We transformed the data into a known data structure that we had, such as elements, which identified the primary data, such as encounters and patients and diagnosis, etc. And then each one of those elements, they had their own set of attributes or the characteristics that was unique to that particular element, such as diagnosis codes were unique to that, as encounter information was a little bit different. And so that way we could store all of this data, and we had it in a known structure. So the first thing we did was perform ETL on the data, and that was typically the largest portion of the time involved in the whole cycle because of the amount of data. But once we got it into the known data structure, we were able to perform a calculation in about 1 to 2 hours. And then there was another process that followed afterwards for some analysis on the results so that we could prepare it for reporting. Now, this is, I should set some expectations on this. What I'm about to show you is not a treatise on SQL Server internals. This is not a step-by-step set of instructions, and it's not some tome of DBA black magic. I am not a DBA. It's all I can do to spell DBA. So I'm not going to try and step on those toes. But what this is just some lessons that are learned from the trenches of working in this environment, taking a look at the data architecture techniques that we used, the database programming techniques, and hopefully this will be a good starting point for you in the right direction. So the first thing I want to cover is the table structures. It's okay to restructure your data for analysis purposes. A lot of people seem to think that the data that we got coming in, that the structure that it has is somehow sacred and it is not subject to change. That is not true. It is okay to change your data for your analysis purposes. If it's more efficient to break a long record into many tables with with shorter columns, do it. It's okay. A lot of people also get hung up on normalization, thinking that we always got to have everything in third normal form. Well, as you're aware, in data warehousing, a lot of that data is not normalized, and it's not normalized to improve speed of querying. Don't need to join 5 and 6 different tables just to get the data. If you can do it once when creating your tables, as you change from your original data structure to your optimized one for analysis, it's okay to denormalize that if necessary. It's always subjective and to the needs of the project. You also want to be sure to handle only the data that's necessary. For example, that one for the healthcare claims, when they copied over the claim header and the claim details, they copied over everything. And I'd say a good 80% of that data or more was never ever looked at. And so all it did was take up space and get in the way of accessing the data that you really needed. So minimize what data you have in a table, the number of tables you have, and the number and size of your columns. I've seen column definitions that were really too large, and most of the data you had to do string manipulation on to get what you needed. If that's the case, then transform it into a better data structure for your processing. Also, take a look at your table keys. I'm a big believer in using surrogate keys. I use big int values when you're dealing with large volumes of data. That way you can avoid using text keys. And you definitely, for sure, do not want to use GUIDs as keys, because the random nature of GUIDs really does a number with your indexes, and it will cause a lot of index fragmentation and wasted time in inserting the records and searching for them. Another technique that I use is to replace key text search values with a numeric ID. So I would have a table that I used for my text values. And as I inserted them into that table, they got a unique identifier, or not identifier, but a unique number that was assigned to that. And then I would use that number afterwards instead of the text itself. What made it even more complicated is that in healthcare, again, we refer to taxonomy and term as a pair of strings. And so, again, the taxonomy is the coding system, and each term has a specific value within that coding system. And as they're strings, you don't want to have searches on 2 text strings for every record in your data, because that will really slow it down. So what I did is I created a table that I stored in every unique combination of those 2 strings. And that way I could have an identifier for that combo. And then I used that identifier in all of my search criteria. And it made the performance go really through the roof on that. Just on that change alone, improved performance dramatically. Also in healthcare, we would identify a value set, which was a collection of those taxonomy and term pairs. And then so we could say, well, here is a value set that identifies a diagnosis of diabetes. So no matter what the coding system was and what terms it used for that, we put that into the value set. And then we could do set-based comparisons on that data to identify the particular records that we wanted. And then we could also use that in multiple measures, so it became even much better value afterwards. So in our table structure, we had a primary data object, which is our element. And then each element was known by a specific element type. So for example, we could say, this was a procedure, this was a diagnosis, etc. And each element could also be identified by tax term pair ID. So if we were looking for a diagnosis of particular types, then we could search for that. And then each element had 0 or more attributes additional to that we could have associated to it. So all the instances of an element existed in the element pool. This is where I brought in all the data. This became like my collection of all the data that we wanted to be able to search through. And then the attributes themselves were related to the elements. And they were also known by specific attribute type because there were many different types of attributes. They could also have been identified by a tax term pair ID. So, to make it even more complicated. And then an attribute type could be used by more than one element type. So in other words, I could have a diagnosis that looked for a particular date, such as it could have a date timestamp for when that diagnosis was performed. Same thing with a procedure. It would have a date timestamp for when that was performed. And so that attribute was shared amongst both of those elements. And then each attribute instance was specific to a particular element instance. So we had multiple levels of associations there. So let me show you a picture. It might help make it easier. So we get our data source, and that comes in. We split that out into our elements and attributes. And then the element was the definition, and then the element pool was this, the location where we stored all of the instances of those records. And then each element pool record was associated to one or more attribute pool records that were then defined by this attribute. And then they could also, either the element or the attribute could be identified by a text term pair. So we took that taxonomy and that term, generated a text term pair ID that we then associated to them. And again, value sets could identify a whole classification of text term pairs. And then we identified that combination set. Once we took that value set itself, I associated it to the text term pairs, and we created a value set pair table that represented everything that we would want to search for. Then we could associate that back to the element and attribute pools. So when we executed our queries, we did so in a set-based manner. It was very, very important because when you're dealing with large volumes of data that you use sets whenever possible. So avoid scalar user-defined functions, because while it may look like it's a set-based query, they can actually break set operations and basically turn your set-based query into a loop. Instead, we used inline table value functions instead of scalar functions. Also, you want to avoid cursors. Most cursors can be avoided by using sets. Now, I'm not saying all cases, that's true, but it can be in many cases. We also used the tally table to replace many instances of loops because, again, SQL Server is oriented towards set processing, not procedural. Some loops we can't avoid, but I would still use them for small iterations. Windowing functions. Windowing functions will be your best friend by avoiding loops and cursors, because you can then get group by characteristics without losing details. Such, for example, you can get a running sum of values. You can get use the row number function. You can use the dense rank and get a lot of value in using those by those window functions. So look those up if you have questions on that. One thing you want to avoid with large volumes of data is complex views. The optimizer, it can only do so much. I mean, especially when you have views that reference views, etc. And I've seen situations where a view would have certain operations that it would perform on, like it would create some computed columns, and then another view references that, and then a query references that other view. Well, because those views are being activated, those computations are still being performed, even though the query that called the second view doesn't even care about it. So be careful with those. Also, complex queries can cause memory problems with large data sets. So what I discovered is that by breaking up the queries into manageable chunks, it resolved a lot of memory issues. So take advantage of the set operators, union all, intersect, and except. One of the bonuses you get out of that is that it encourages parallelism. So if as many CPUs as you have in your server, it will then split out each of those queries that you say you have 10 queries that are put together with union operators, and then it will spread those out and run them in parallel. You can also take OR conditions that would be in your where clause or in your join clauses, and you can separate that into separate queries and then union the results together. Then you get your parallelization, and it allows you to make better use of your indexes, because OR conditions are too ambivalent for indexes to be used effectively. But if I have a situation where I have query A and then query B, and I union the results together, that's better than saying one query with I have a where clause where it's an A or B situation. You want to avoid the use of distinct in your queries. Uh, I've seen this used and overused too many times. It's pretty expensive in your query processing because there is an implicit sort. Whether you really wanted the sort or not, it's going to perform a sort in your data. And too often it's used to cover up poorly written queries because they return duplicate rows, and so people will then throw a distinct in there. There are other options that are better, such as the row number, which is one of the windowing functions I mentioned, that will allow you to identify the number of times that those records occur, and then just select the ones where row number equals 1. That way you get the benefit of the distinct without performing a sort. Looking at the joins in the tables, a lot of times people that use left joins want to do that because they want to handle a type of an OR condition. Again, those can be rewritten to be separate queries, and that would improve your performance. Query hints may sometimes be necessary to encourage hash joins with large data sets, but I'd caution using that all the time. You also want to avoid the use of outer joins with large data sets. They perform really poorly just because of the combinations of the data. And sometimes it also pulls in extra data that you then have to turn around and filter out for your final results. Those can usually be done with a set of multiple queries that you union the results together instead of performing an outer join. In working with the large data sets, I've never seen a need where I had to use an outer join. I was always able to do it with multiple queries. Avoid calculated fields in your join and where clauses. While they're awfully handy, the problem is that it can cause your indexes not to be used when you would think that it would be used, because they're not discrete values, and so the indexes don't know what to expect, so the optimizer will ignore them instead. It also causes extra processing for each of your calculations. So what I tended to do was pre-calculate the data in another table or in a CTE before I executed my query, and that improved performance. So take a look at your explicit transactions. I found that by using explicit transactions, it improved performance because I was able to take, instead of an entire large store procedure and while it's running, I could do implicit transactions throughout there, and it allowed the system to identify logical units of work and free up system resources, so that instead of waiting till the end of the store procedure to release all the resources, because then that way, if I was done with, say I had 3 parts to it, and part 1 I was done, release the system resources, then do part 2, and release those, and then do part 3. Also, you want to minimize the nested transactions, because again, that causes system resources to get locked up, because when you have a transaction in process and then you start another transaction within that, it is still nested within the outer transaction. So that can cause resources to get locked. Store procedure calls. I found that avoiding deeply nested store procedures was really helpful to performance. I've seen code that was developed by .NET developers, and they tended to treat store procedures like they would C#, and it doesn't work as well. This isn't C#, so sometimes you want to a larger store procedure is better than having a lot of short store procedures, but a lot of calls to store procedures. because it causes memory issues. You also want to avoid complicated parameters. I've seen store procedures that had a dozen different parameters, and that caused problems. I'm assuming it's because of the impact of memory. I found that when I reduced that, it made it a whole lot easier. And I also minimized the number and the size of output parameters. I don't have an explanation for why that really helped, but it sure did. Take a look at your execution plans. They are very much subject to change. You've heard the expression that it worked in the development environment, but that execution plan or that query may not work well in production because it will change. As your data volume increases, your queries may need to be rewritten or tuned to accommodate for that data volume. I'm going to cover partitions. I know it's not really part of indexes, but it is in a kind of a logical way. Many of us don't use partitions because we never think about it, but they do identify discrete and non-overlapping data sets that you can break apart, and you can segment your data into those defined chunks so that when you go to the optimizer goes to look at the data, if it's not going to access certain partitions, it won't even bother searching the indexes for that, so that those indexes will be broken up into those partitions. It also allows you to take the data and place it in different disks, different areas that to help improve performance. And it also makes maintenance a lot easier too, because then you can delete data or insert data in only a given partition. Take a look at your indexes. Make use of covering indexes where it's appropriate, so you don't have to go back and query the table as well as the index. Avoid being overzealous index generators. I've seen people, just because the query hint said that we needed an index, they created an index, and so they had more indexes than they did columns in the table, and that was not helpful. That really slows things down. Take a look at your joins and your where clauses. Base your indexes upon those, the conditions that exist there, and then periodically reevaluate your indexes. If there are indexes that aren't being used or minimally used, it's okay to drop them and get them out of there, because that way the system doesn't have to keep maintaining them. And there are good cases that on work tables or tables where you're not doing much processing other than reading and writing, it's okay not to have any indexes or foreign key constraints on those. Now, we did take a look at some alternatives for doing all of this. For example, in column store indexes, it's a cool idea. Unfortunately, we implemented this system on SQL Server 2008. And even then, in the 2012 version, it wasn't as good as it is now in the 2016 and 2017 editions of SQL Server. Unfortunately, they also don't retain the relationship between columns. So while it's really, really great at finding particular data that's in the column store index, if you're looking for additional data in that table, it's not going to help you there. Column store indexes do a deduplication process, and I did take advantage of that kind of an idea where I deduplicated data that was being stored for the measure results, and that improved performance. So I did kind of borrow that concept. Why didn't we use another platform instead of SQL Server? We could have used Hadoop, but the data was highly relational, and it required constant updates and deletes. So Hadoop is not designed for that, so therefore we didn't use that as an option. An MPP system, or massively parallel processing. We did do a port from the SQL Server system to Netezza. That was a bit of a challenge because Netezza operates a bit differently and has some different concepts that aren't found in SQL Server. But it was very possible. We did it, and it works quite well. We could have done Teradata as well, and it would have probably been an easier port. Uh, we could look at multiple SQL Server instances. We could have replicated the data amongst multiple servers and sharded the data, kind of like what the MongoDB does and Hadoop. Then we could have combined the results at the reporting server, but there would have been a lot of overhead in managing that data, and yeah, I don't think it would have been worth the hassle. We were able to get the performance that we needed on the single SQL Server instance. So just some closing thoughts on here is that NoSQL big data environments, it relies upon sharding and parallelism for the performance. It is not relational, and it doesn't perform in the same way that SQL Server does. But it does handle unique data environments. It's really, really effective on non-discrete or unstructured data for storing it. It's designed for storing and fetching data, but it's not for updates and deletes. NoSQL environments do not have a built-in query tool or language. And while many of them use or have a SQL environment that is attached to it, it's still not part of the database itself. And so all data processing is done outside of the database. While it does allow for complex procedural algorithms and programming, there are things that you can do in a procedural code that will run rings around SQL Server, such as text processing and stuff of that nature. So those are benefits to that, and there are multiple tools available to do that type of data processing. So that's one thing that NoSQL environments do have, is that big palette of choices available. But it's not a relational database engine. And again, those SQL interfaces are there for convenience. I've seen people use them in a production environment, and they were not designed for production. They were designed for people to go in and write queries to answer questions that they needed at the moment, not for doing all their production processing in it. The tools are improving, but they are not optimized for relational queries because that's not what they're designed for. The SQL Server, it is a true relational database engine, obviously. It's designed to perform updates and deletes. And it performs even better when you use set-based logic. It is designed to work with structured high-volume data. It does not do well with unstructured data. And so that's where, as I mentioned before, there's been a synergy between Hadoop and SQL Server, where you can use Hadoop to store the unstructured data, and then what you're able to glean the structured data from that, store it into SQL Server, and then do processing. T-SQL performs data processing close to the data. That's one of the reasons why it is more efficient than using an outside processing system such as .NET or something, because it's right there in the data itself. But it is limited to a single server, so that becomes a problem. But if you really wanted a multi-server environment, that's SQL Server, that's Azure. It's multi-server SQL Server in the cloud. Are there any questions?
Yeah, we got a bunch of them. Michael was asking, how did your company manage the value set for different diagnosis procedures?
We actually, there is a library that's managed by the Library of Medicine, Congressional Library of Medicine, for value sets for what is determined to be standard. And so we would take downloads from that value set library and then import those into our system, and then again assign those unique identifiers for the combination. And that's what we used to manage them. Fortunately, we didn't have to come up with what those code values were. They were done for us. We just had to implement them.
So how often do you guys implement that?
The measure changes occurred at a pretty regularly scheduled basis, and so when a change was published, then we would import those changes into our system.
So how did you guys find out when or when something's changed?
There were email notifications sent out, that we actually subscribed to the notifications that when the measures were changed. And because of the process and getting those measures approved, they changed, at most twice a year.
Oh,
Usually they were only once a year, but yeah, it's not like that they changed all the time. Now, if there were custom measures that a client could write their own custom measure, then they would implement that, themselves as they needed, and that was the whole benefit of the system, with allowing them to take that measure definition and compile it into a stored procedure.
cool. Another question is any public guideline or reference related to those value set?
Yes, there are, and that's probably a much larger discussion than to carry here, but the Library of Medicine does have quite a bit of guidelines and how they're used in the clinical quality measures. That's something that the CMS and the other organizations like that maintain.
So when working with the unstructured data, with SQL Server has a lot of null value, so the volume is very big.
About the most unstructured data that we handled were for like X-rays and other types of images, or like ultrasound data, etc. We just stored it. We didn't do any processing with it.
So in the case of minimizing nested transactions, do you suggest using temp tables to set up the same situations?
I actually, instead of using temp tables, I had a set of tables in a separate schema that I created and used over and over again, instead of using temp tables. The reason for that is because in this type of processing, I didn't have to worry about concurrency. I didn't have to worry about user A running the same program, a system as user B. And so I used static work tables, and it was actually more efficient that way.
Okay, sounds good. How about MySQL? Does MySQL also work in big data environment? And if so, what is the difference between SQL Server and MySQL in big data?
I have seen situations of MySQL being used along with Hadoop. I'm not as familiar with MySQL. I've only dabbled in it. It's loosely based on the same type of structure that Oracle has. And so I don't see any reason why it couldn't perform on that. I just don't think it has the steadiness of SQL Server and the rock solidness that SQL Server has to be able to handle such large volumes.
How to tune the stored procedure that are tested perfectly in the dev but run poorly in prod in terms of big volume in prod?
Yeah, we actually kept a table of how to put this. I would log queries that occurred in the store procedures, and then we would enable that logging in a production environment where we knew that it was having some problems, so we could capture what type of data volumes we had for particular queries, what their record counts were, what their execution times were, and so we could pinpoint where the problems were. Sometimes it would come down to a particular query within a store procedure and the fact that it was having the wrong execution plan.
Okay. When I use data in Hadoop to produce report, do I need first to transform Hadoop data into relational database to do report?
Um, it depends on if the end result of that data is relational, then definitely I would export it into a relational into the SQL Server for reporting purposes. Most reports are relational by nature.
Mm-hmm. Yeah. Is big data structure similar to with something like Dynamo DB in AWS?
I'm not familiar with that well enough to answer that. Sorry.
Okay.
I mean,
Store.
I'm currently using SQL Server in AWS, but um, not the dynamic aspects of it. They're just hosted systems.
Okay. Storing those library of Congress codes, are there a lot of codes? Did you say you also store the description along with the code as well? If not, then still have to do join to pull in the description to show up in the report, right?
Uh, we didn't actually use the descriptions that were in the codes because that wasn't the focus of the data. We were after the relationship between the taxonomy and the term itself, and what was used to identify. We would say here is a set of codes to identify this particular situation, and so we would then look for the records that matched that. We didn't really use the descriptions, but you're right. There is a ton of values out there, especially like when you're looking at ICD-10. I mean, the thousands of records out there for those descriptions. Um, Fortunately, it was something I didn't have to deal with.
Yeah. So somebody was asking you if you have a blog or website.
I do, and I'm going to show that. I started it up not too long ago. It's uh, having the time to do that is one of the things I'm having to struggle with to make that more active. But it's been my goal this year to do that. So
Yeah.
I'll share that here in just a second.
Okay. Yeah, they also want to connect you, and they also wondering if any books you would recommend.
Uh, I would love to recommend some books, but I had difficulty finding them myself. Most of this, what I've presented on this was from my own experience. So
Yeah.
other than the links that they're in the slides, I don't have anything else to share on that. But speaking of books, I do have some links here to some free ebooks from Microsoft, Redgate, and Century One. So you can share that in with the links.
Yeah, I'll put it on our website. Yeah, that's great information. So this other one, ICD-10 is now supposed to be upgraded to ICD-11, which is even more complicated.
Yep.
Oh, I guess it's just a comment. So talking about the SQL Server in AWS, what is the strength of SQL Server in the cloud?
um, I I, our current environment where I'm at now, we use again all of our SQL Server environments are in AWS, and we've not had any problems with it. It's actually kind of convenient because we can spin them up or spin them down as we need. So it makes it really great. So we can spin up a test environment. We want to, move some data into it, and just it's like having a virtual machine that you can just spin up as needed. So
Mm-hmm.
that's pretty cool.
Yeah. So, yeah, Alex also is asking government regulation mandated ICD 10 upgraded to ICD 11 a couple of years ago.
Yeah, unfortunately, it was funny because with the ICD 10 upgrade, when it went from 9 to 10, CMS was really pushing vendors and hospitals and all to get ready and requiring them to be ready by a given date. And then within a few months of that date coming, CMS put out an extension to it. Well, the real story was that they weren't ready for it yet. So they pushed it out because they weren't ready, and yet they were going to hold everyone else to that date. So I thought that was kind of funny.
Yeah,
But
that's funny.
I have a feeling that I don't think ICD 11 will take as long as it did for 10, because now that that paradigm shift changed, 11 will be able to be implemented a lot sooner.
Cool. Um, I
Hey, I
don't
have
have.
a questions.
Go
Sarah,
ahead.
I have a questions. Hey, Ren, I have a questions about how you handle the healthcare sensitive data in cloud.
For sensitive data, uh,
Yeah.
it, just because a server, you put your data in a server and it's in the cloud doesn't mean that it's out there for everyone to look at. It's still secure. You still have your same security requirements. Access to it, is limited. Not even your cloud host environment is allowed to have access to it by definition. So
Okay.
whether you use Rackspace or Amazon or whoever, when they host your environment, it's your environment, your data. They cannot access it.
Got it. So the old process is same, just move the space from rack to the cloud, right?
Right. It's no different really than, let's say that, your company wants to host their own environment. So they build a data center somewhere and everyone connects to that data center through VPN connections through the
Mm-hmm.
internet. It's no different than that. That then becomes a private cloud.
Mm-hmm. Got it. Thank you.
Okay, Lucy, I see you raise your hand. Do you have a question? I have unmuted you.
Oh no, thank you. I have no question.
Okay. All right. Thanks.
Sarah, they have other questions from Alice.
Yeah, I saw that one. But Lucy hand has been sitting there for a while. That's why. Uh, all right. The Alex was asking, what usually do you write stored procedures for?
Uh, I use store procedures for all data manipulation whenever possible. I don't like to have if you have a middle tier environment, for example, if you have let's say you're using a web application, and then you connect the web application to a middle tier environment that does all of your C sharp heavy lifting, etc. And then I want that to make the calls to a store procedure in SQL Server instead of it doing the updates or inserts or deletes. Have a store procedure do that, because you can lock that in more tightly. You have your SQL Server permissions that can be locked down, and it's just much more secure. That way, you don't have the SQL injections or any worries or issues with that.
Right. So in that case, would you just have say like all of your users are using the same service account or something to call that store procedure right into your database, or you have everybody can just call the store procedure directly and right into the database?
No, the users have access to the middle tier only. The middle tier is the one that makes the call to the store procedure. That way, it's locked down to a service account.
Okay, similar like a gateway or something.
Right. And
Okay.
now we do pass along the user ID as a parameter to the store procedure so we can track that, who made what call, et cetera, because as you know, with healthcare data, you have to, be mindful of that for HIPAA compliance.
Mm-hmm. So is it possible, like, uh, you know, uh, okay, so in that case, you compare that the person who made the call to that store procedure with your, say, like AD group or something, to make sure, okay, that's a legitimate person to use that.
Right. The middle tier is the one that handles whether that call is legitimate, because
Mm-hmm.
we will have, in the database, it'll when a user connects to the application, the middle tier say, okay, here's this user, and it executes a store procedure on the database that says, is this user allowed to do this? And if so, the database will then log the login, return back the status, and then the user can go on and do its thing. And then all of those, every activity that the user performs, again, goes to that middle tier. The middle tier passes it on to the database and representing the user. And then that way if we can handle multiple logins at the same time, multiple people, the database doesn't care who's doing it because it only deals with the middle tier.
Yeah, so everybody's dealing with the middle tier, but with so many people, say like they're all inserting at the same time, or and only use the middle tier, probably just is one account that writes to the database. Would that cause traffic, like conjunction or something?
It sometimes can, but it's not because of it's a one user account. You still have your each session that the middle tier connects to the database with is a separate session. And so, the SQL Server is very good at handling concurrency. In fact, that's why it excels at those types of transactions, because it's a transactional environment.
Okay. Okay, so you mentioned the design is normalized, but not totally normalized.
Right. I mean, like for example, the issue I presented with the taxonomy and terms. You saw that I created a separate table for that, and I created. I wouldn't even call that normalized, but that was done for efficiency in translating two text fields into a single numeric value, not necessarily for normalization. There are some other areas where I replicated data during processing, so that I didn't have to go back and look it up. So I'd had fewer joins during the query executions. So if the data doesn't change, if it's going to be like, let's say that, every time I query table A, I need columns 1, 2, and 3. Well, it's okay to replicate that over whenever I always join it with table 2 or, table B, because then as long as that doesn't change on me, I can replicate it and denormalize it to improve query performance.
Mm-hmm. Also, another question followed by that is hybrid. I think there's a typo here. Hybrid third normal format and dimensional design. I
Yes,
guess.
actually, I've had people look at my database design and say that it had functions of both a transactional environment and a data warehouse. And so that was probably, it's a very accurate way of looking at it. It was a hybrid environment, and it worked well.
Well, would you be able to elaborate that? How on which end it's the transactional, the other end is the data warehouse.
Okay, the transactional part is the when we imported data into from the original data source of the clinical data, and we broke it out into elements and attributes. When we performed the measure calculation itself, it was more transactional because we would be looking at a particular measure at a time. Now, we were doing all patients that fit. So, and it was still kind of, it was still transactional because we were doing each step one after the other when performing the measure calculations. So that was more transactional. But when we transformed the results of that for analysis, that became more of the data warehouse part.
Gotcha.
Where we would take that and prepare it so that the reports could then have the results for their pie charts and bar charts and all that other analysis that was performed on it. That was the transition from transactional to data warehouse. The other aspect that was like a data warehouse is, like I said, with the denormalization, so that when we perform these transformations during the execution of the store procedures, it was more data warehouse type environment. So it's really hard to say where the line was because it was just kind of a gray area.
Yeah.
Where some aspects were more transactional, some others were more data warehouse.
Yeah. Okay. Alex also asked any snowflake dimension used in what way?
There may have been. I think I didn't design it to be like a data warehouse intentionally. It just grew out of that, and by the nature of the beast. So I'm not sure if there were any snowflake dimension designs in there. It was accidental.
I have a good question. When you mentioned not to use GUID,
yes,
and replace it with a surrogate K, so when you replace it, you just use the identity or something?
Yes, I used identity values and used on big ints. The main reason to have a primary key on a record is so that when you create your indexes, it say that I have I just call it column A is my primary key, and it's a big int. And then whenever I reference, have an index on column B, it will always by default include the primary key as like a covering field in the index. So that's why you always want to have a unique key on there for that primary key, and so that it will always make reference back to that row. And by doing it with a numeric value, especially a unique numeric value, it made the indexes far more efficient. Had we stuck with a text value, for example, even if they were all unique, it would have had more processing to do in order to confirm that that was a match.
Right.
Because numeric matches are much faster.
Absolutely. So would you think it'll be a good idea to create like some kind of lookup table to, match the GUID with a number? Something?
You could. Well, I mean, GUIDs themselves are numeric. They're just really large numbers. The problem with GUIDs is that when they're generated, they're usually done not in sequence. And so that's why I don't like to use them for indexes and for primary keys, because one, they're very large, and two is because they're basically random. And so you get a lot of index fragmentation.
Okay.
And so when you go to match them, it makes it very difficult, because now you're having to match two large fields together that don't sort well in the index.
Yeah. Yeah.
But
Go ahead. Sorry.
I'm saying, but by using identity values in a big int, it's still large enough to handle the volume of records that you would need, but it's a numeric value that is easily compared to another numeric value, and so it performs much faster.
Yeah, makes sense. Yeah, the GUID in my world is a combination of numbers and letters. So yeah.
Yeah, and that's the way it's usually represented for us to more easily read it. But internally, it's stored in a numeric fashion.
Okay. Any more questions from the audience? I think that's all we have. Yeah. Thank you so much. It's over an hour and 46 minutes. It's a long session.
Yeah, it's no problem. Yeah, if there are any other questions, feel free to contact me I got my contact info there, and I would appreciate some feedback on the presentation for what worked, what didn't, so I can do a better job next time.
Oh yeah, I'll collect feedback and email you if that's okay.
Yep, that'd be great. Thank you.
Okay. Thank you so much, Aaron. Spend so much time and be so patient in asking and answering all our questions.
Not a problem. It was fun. Take care, and I appreciate everyone spending their time with me.
Thank you so much. Thanks to everybody for attending and asking all those good questions. This session is recorded. I'll post the recording tomorrow. And Aaron, if you can send me the slide deck, I'll post it on our website as well.
I will do that. Thank you.
Okay, thank you, everybody. Goodbye, and hopefully I see you on our next session.
Thank you, Aaron. Thank you.
Thank you. Bye-bye.
Bye.